My name is bobolen, and the topic that I'm going to be discussing for my final project is microfluidics. As defined by the online journal Microfluidics and Nanofluidics, microfluidics is the study of mass, including molecular and colloidal, and momentum transfer, heat transfer, and reactive processes coupled with transport in microscale and nanoscale systems. As I've studied this, what I've come to realize that microfluidics means in layman's term is just the ability to manipulate liquids at the micro scale level, often dealing with liquids that are in the picoliter scale. So it also has to deal with how you manufacture devices that can deal with that level of liquids, and the processes that are involved in that, and just other research. And it's very interdisciplinary due to the fact that there's very many applications for microfluidics across many different fields. And that's what I talk about here is the next is the research field. So microfluidics is still in its infancy, but even in its infancy, we're already seeing multiple fields that have applications for microfluidics. Just to name a few, and the four biggest ones that I saw that have wide-scale applications of microfluidics is aerospace technology, computer technology, automotive technology, and biomedical applications, with biomedical applications by far being the biggest industry that has taken a hold to microfluidics and the possibilities of this technology and what they can do with it in their fields. So for the remainder, for most of this slideshow, I'll be talking about microfluidics in biomedical applications and what has been able to be accomplished with it. So biomedical applications, when you think of them on the regarding microfluidics, you really come across one thing, and it's called lab on a chip, or LOAC, that I've got it labeled here for the rest of the slideshow. Basically, what lab on a chip is it uses microfluidics devices, microfluidics principles in order to create some biosensing systems. This is really if the point of care model is ever going to work, it really is largely dependent on these lab on a chip systems, because the whole point of point of care, this point of care process and point of care way that they're going to do things, it's really dependent on being able to do diagnostics without expensive machinery, without expensive labs, without imaging technologies such as MRIs or X-rays, and that's what lab on a chip really does. Is it incorporates microfluidics in order to be able to diagnose patients without all the expensive equipment and labs and stuff that is typically needed to make those diagnoses today. So there's many different lab on a chip manufacturing techniques, and the biggest one being, especially now, they're starting to come up with a lot of research, but the biggest one that they use is silicon as the base for lab on a chip systems. I mean, there's advantages to all of these that are on here, such as glass and thermopolymers, or PDMS and paper. And you think of glass and thermopolymers; those are clear. So there's advantages in certain situations where you want to use clear polymers, where there's certain certain times we're going to use like silicone. The reason why silicone is becoming more popular is because there's already photolithographic processes that deal with silicon-based structures. I think when you think about CMOS, it's just rather than using them to create electrical devices, just transistors and whatever it is that you need to create, they're using the silicon base in order to create mechanical devices like these microfluidic devices that can do mechanical that has mechanical properties and can do mechanical functions that just aren't able to be done today without microfluidics. So there's some benefits to lab on a chip systems, and I mentioned a couple, such as like low cost, because you have to think about the cost of the alternative or the traditional way of making diagnostics, which such as having expensive labs, having technicians to run those labs, having expensive imaging hardware and software, such as MRIs and CT scans. Like I said, the point of care isn't going to work unless you really utilize these alternative ways of diagnosing diseases without that expensive machinery. So hospitals around the world that can't have an MRI machine or an X-ray machine, these lab on a chip systems are really going to be beneficial to those. Just when you think of a cost-wise one. But another benefit that lab on a chip systems have is they can detect small amounts of pathogenic bacteria in foods, bodily fluids, tissues, samples, etc. And they can do it with a low volume sample. So rather than needing liters and liters or kilograms of soil or what you would need, you would just need a small amount. I mean, like I said earlier, this microfluidics deals with picoliters, typically with picoliter levels of fluid. So as long as the sample, the microfluidic sample that you're taking is a representative sample of the entire culture that you want, it's going to be able to make the diagnostics, find the amount of bacteria, or find whatever it is that you would need to find, as long as, like I said, as long as the sample is truly representative of the entire sample space. Another big thing that we're seeing is there's very high parallelization. So you can, with one sample, you can do a myriad of things with a myriad of tests with these microfluidic devices at the same time or one after another if you need to, because of the ability to stack the microfluidic devices one after another, one on top of each other, and you'll be able to do multiple tests with multiple different microfluidic devices at the same time or relatively at the same time. So those are just some benefits of lab on a chip systems. There's also setbacks to lab on a chip systems, such as the no growth step. So when we need to find if there's been bacteria in soil, or if there is, if you have a bacterial infection, then obviously that bacteria needs to be alive in the sample that you're taking. So one setback, and then they're working on research to get around this, but one setback that they have right now is there's no growth step. So what that means is if the bacteria was alive in the sample that you took, then you need it alive in order to say definitively that this bacteria or this soil or this your body tissue has been infected with this bacteria because it's alive, and it was alive when it was in you, and it's still alive because of this growth step. But currently the problem is they need to process the samples very quickly, or else this bacteria will die, and they won't be able to say definitively that the bacteria was in the sample that they collected. I mean, it could have been in the sample dead, but the dead bacteria doesn't cause too much problems as much as live bacteria does, because live bacteria multiplies, and that's where you get infections. There's also Microfluidic systems also require exterior systems to work. So they're not self-contained. They need exterior input. So it needs devices that can push um, microfluidic levels of fluid through the systems in order to run the tests, and that's something that they're not able to do by themselves yet. So they are a dependent system, very beneficial, but they are dependent on outside systems for them to work correctly. Another setback is they're not ready for industrialization, and there's just with some, not all microfluidic devices, the signal to noise ratio is not the best. Like I said, that's for some of them and not all of them, but that's another setback of lab-on-a-chip systems. As far as not being ready for industrialization, I'll go through it a little bit later, but they are coming up with research in order to ready the microfluidic devices for more industrialization. Now, for a specific lab-on-a-chip example, there's an article that I read where they are using microfluidic devices and lab-on-a-chip systems in order to help diagnose a type of coronary artery disease. Not that should be CAD, not CSA. So there's typically two classes of coronary artery diseases: chronic stable angina pectoris, and that's detectable using electrocardiograms and such traditional techniques that are available today. But there's another class called unstable angina, and these are not detectable using the electrocardiograms and the traditional techniques that we have so far. It's dangerous because the patients that have these kind of diseases, they definitely experience all the symptoms. They have all the warning signs of coronary artery disease, but their test will more often than not come up negative for coronary artery disease. And that's where scientists are starting to use lab-on-a-chip systems in order to detect unstable angina, and unstable angina type of coronary artery diseases. And as they continue to do research, they're starting to become more successful and at diagnosing these classes of coronary artery diseases. So it'll be only a matter of time before we start to see lab-on-a-chip systems more widely used with reference to diagnosing these kinds of diseases. Another area that's receiving a lot of research is the manufacturing research. So this has to deal with not being ready for the industrialization of microfluidic devices and lab-on-a-chip systems, and that has to do with the fact that the fabrication processes that are available today for creating these lab-on-a-chip systems and microfluidic devices, they're very specialized for every single device. So if a fab wanted to change up what microfluidic devices that they were creating, they would need to restructure all of their processes that they have. So one article that I read is they are using silicon on insulator based devices in order to more widely to use photolithographic processes in a more general sense in order to basically plug and play which microfluidic device they wanted to use. Now they haven't been able to create a process that's one process that'll create any microfluidic device that you want, but they're starting to come up with research that'll allow a single process with minor modifications to be able to create many different microfluidic devices, and I think that's the first step. Well, it is the first step for becoming ready to industrialize these microfluidic devices. It'll also, as the cost continues, as the process continues to drive down the cost per per device, it'll obviously lower the overall cost of these microfluidic devices, which will even which will just drive the demand up even more for lab-on-a-chip systems and just other microfluidic devices across many different fields. So these are just a few research areas that are happening right now in the field of microfluidics, and as we continue to go through, as research continues to happen on all of these devices, we'll see that there's going to be a lot more industries that will adapt microfluidics for their specific industry problems, and we'll see the processes continue to get better. Here's just some of the sources that I used in here. In my research article, there's even more sources listed. I hope that you enjoyed this little presentation on microfluidics, and I know that as the industry continues to get better, we'll just see more and more microfluidic devices in our everyday lives. Thank you.